Good morning. It's my honor to present a lecture at Hopkins. I would like to take the opportunity and to express our extreme appreciation for the hosting and the exchange program. Once I was young or younger, I was the issue of artificial intelligence was a mystery for me, and I was very much keen on knowing how we can artifactually develop an intelligence. Recently, we have published an article in the Journal of Cataract and Refractive Surgery in which we used artificial intelligence and machine learning to predict the risk of posterior capsule opacification. I actually delivered some reprints to be distributed in case you wanted the details of the study. We know some facts about PCO. Despite efforts we made, it happens in almost 20% of the post-operative cases, when of course it depends on the time course that you consider. And we have identified some of the risk factors, like the age, the female gender, diabetes mellitus, pseudoexfoliation, and also the length of the eye. Before going forward, I would like to review the scope of observational research. The first and the least, or probably the primitive objective of an observational research is to describe and explore. When the evidence is scanned, what we can do is to describe and explore. The next level is the explanatory research that we are much accustomed to, in which we have some kind of hypothesis to be tested. That is called explanatory research. And then it comes to prediction. That is the main objective, because we want to plan the treatment, we want to plan the follow-up, and we want to provide the prognosis. And that is this needs prediction research. This is done with statistical modeling. I mean, prediction is done by statistical modeling, simulation, and of course experimentation. That is out of the scope of observational research, but anyway, we can through experiments we can again make predictions. The whole thing is in artificial intelligence and modeling is that we are trying to formalize the relationships in the form of some mathematical equations. And these mathematical equations could be as simple as linear equations that we are well informed, like regression formula. Or it could be very much complex that cannot be easily probably written on a sheet of paper. The literature on application of artificial intelligence in ophthalmology is not much, and I listed some of them here. It has been used for glaucoma diagnosis, for the prediction of survival in choroidal melanoma, and also in diagnosis of different types of corneal topographies, and especially keratoconus in the earlier stages. We had in our study we had almost 350 cases who has been operated on for age-related cataract, underwent phacoemulsification, and we examined them 2 years post-op. Some of them had capsulotomies, had capsulotomy at the time of the visit, and some of them had needed such a procedure. And there was 40 eyes like that. We, of course, I should say they had visually significant posterior capsular opacification. We listed and used 10 potential determinants in order to evaluate, make our modeling, and actually develop the network, the artificial neural network that are listed here. Well, of course, the list is not comprehensive, and I will tell you sometime later that this actually constitutes one of the major limitations of our study. By surgically challenging eye, we meant having a visually significant corneal opacity, a small pupil, or phacodonesis, and situations like this. Well, this is the sample decision tree that we succeed to develop. And as you see, we used the algorithm is called Quest algorithm by the software Clementine. There are lots of data mining softwares that especially engineers are well versed with. In fact, artificial intelligence and machine learning is a multidisciplinary exercise, and that is the case in our own case. If you see the authors and my co-authors and the institutes, it covers engineering and also some other people who are has the expertise. As you see, in case of decision tree, the software develops rules. You can go through different paths. For instance, it chose the corneal opacity as the major factor to segregate the data. So if there is a corneal opacity, there is a risk of a third of the patients, for instance, would possibly develop visually significant capsular opacity necessitating capsulotomy. And then you can go down different ways to come to, for instance, it's interesting, but of course it might be wrong, but when there is the axial length, say, is over 24.5, that is, if you have axial myopia, and the age is over 65, the gender would be female, and the cataract is not mature, and the corneal opacity, and there is no corneal opacity, then the risk of a visually significant corneal opacity would be 0. These are, actually, this is the result and what decision tree provides us with. In our own case, the accuracy that we reached, it was 50%. The high likelihood ratio was less than 1. It's not a good performance. These are not good indices for a decision tree. And this is an example, as I mentioned. This is a sample decision tree. The next exercise in artificial intelligence that we did was, let me go to the next slide and then come back, where we actually developed a neural network. I just showed this scheme to explain what neural network is and how it really works. My question was that, in the old days, was what are neurons and what are synapses? Well, if you consider that the right side would be the outcome, that is a visually significant capsular opacity. And on the left side, we have the neurons that take the input of the variables I mentioned, like ages, like gender, etc. And in the middle, this is the researcher that sets the architecture of the network, I mean the layers and how they are related to. For instance, if each layer is interconnected or not, or the connections are just vertical. So synapses are the way that the layers are being fed with information. We have, this is the very exercise. We divided the data into two sets, one training set and one test set. In the training stage, we actually fed the network with known factors and known outcome. When the known factors would predict a wrong answer, the answer would be back propagate into the network and changes the coefficients that are in the neurons. So neurons are in fact mathematical functions whose coefficients could be modified and manipulated through learning. And in this slide, you see the performance of three different architectures that we considered. They had 2 hidden levels, all of them, and they had 40, 20, and 4 neurons. As you see, the performance of this structure was different, and we reached the best performance when we considered a 40 neuron architecture, and we reached an area under curve of 0.77 almost, and the likelihood ratio was 8, and the overall accuracy was close to 90%. And these are good, actually, indices for a artificial intelligence model. I don't know if you have remind you of this curve. On the left side, we have sensitivity. This is receiver operating characteristics curve that originally used for radars. And this is a very much useful instrument for clinical research as well, and evaluation of the tests. And a good test is the one that has a very good sensitivity and a very good and a very good specificity at the same time. And you know that in general, when there is a good sensitivity, the specificity would be less, and vice versa. So there is a trade-off. And in this curve, a test that has a rapid growth like this would have the highest area on the curve and would perform better. That is the case for the 14 neuron structure here. I'm sorry for the sophisticated technical terms that is inevitable for the case of artificial neural network, but I would like to emphasize that the concept is really easy to grasp, and I do highly recommend you to consider using artificial intelligence in your future exercises. In fact, we uploaded the module in the internet. This is the domain we registered, PCOprediction.com, and you can go to that area. This is the, I didn't know if we have internet access. That is why I put it here. Well, I can go. Oh, it came. Okay. In this page, in fact, you can enter different factors like, for instance, age. I would say 65, female gender, not pseudoexfoliation. There is a long eye, short eye. And then probably diabetes, yeah, and experienced surgeon. The type of the IL material, say hydrophilic, and non-mature cataract, and a surgically challenging eye. Let's see if the patient would have a visually significant negative. It results in negative. It reports negative. Anyway, it's the way artificial intelligence works. And you can, of course, you can test your real or hypothetical cases in that area. Well, we are working on this network, and we would like to provide probability next to the result, and it is needed because just simply saying that it is negative or positive is not optimal, and we are working on a model to provide the probability as well. In this, actually, last slide, I would like to compare the prediction methodologies and together. You are probably well informed of linear regression, in which we are looking for some gross fit. There is one dependent variable and one actually independent one, and the good thing about linear regression is that the relation is quite simple and could be interpreted easily, and even clinically or epidemiologically it could be interpreted. And it's the relationship that might be encountered or discovered could be used in order for the preventive purposes, not just prediction. Next one is a type of multivariate analysis. Probably the most famous one is logistic regression, in which we are looking for an optimal fit. We can actually examine the interactions or somehow control the interactions, and they are more valid and they got good generalizability. This is in contrast with the neural networks that are looking for the best fits, because in the training phase, the variables and coefficients actually are changing, are quite plastic to optimally fit with the outcome in that data set. This has its downsides. This overfitting would result in a very, very high internal validity at the cost of external validity and the ability to generalize the results. That is the case in our own example as well. Well, decision trees create rules, and they are very intuitive. The two major limitations in our study were the data set size was small, as you saw. It was almost 350. It's small for the practice of artificial intelligence. You should have a bigger data set, a huge data set, but perform quite better. And the next point is that for some of the data that we collected were retrospective, and some of the factors were not actually potential determinants of capsule opacification were not collected. So the framework was not either optimal, and so I cannot say that our neural network could reliably predict. And this is the way I ridicule our own neural network whenever I say that we actually created a relatively not intelligent child, but he got a very good self-esteem. In whatever case you provided him with, would predict for you the risk, but frequently he made mistakes. This is for further reading, and I also distributed the reprints. I would be very much happy if you can comments or questions, and probably now or probably following the lectures. Thank you. Sure.
So, as you go through the future iterations of this project, are you taking into account the specific types of lenses that are being put? Mainly if the shape of the lens is a square edge versus a round edge?
In fact, I can almost claim that it's probably a decade or less than a decade, but including the duration of the time course of the study, that we almost always use a square-edged type of intraocular lenses. But this is actually one of the limitations of our study, because not just the square edge, the being multi-piece or single piece, and the angulation also would affect the rate, and these are the factors that we did our best to collect, but we cannot, because some of the data we had were retrospective.
So where is it that you collected the data from? Within your own hospital?
Yeah. That's right. Actually, the setting is the optimal setting for artificial intelligence to provide an optimal generalizability would be some kind of national registries or interhospital or some type of that. Like, I don't know if you have heard of European Registry for Cataract and Refractive Surgery, Quality of Outcome, something like that. Such a network, such a setting would provide with a huge amount of data, and will probably result in reliable networks or intelligence.